All right, everyone. Second half of our digital video practical or lecture. I hope that you have maybe an R file open and downloaded the data and try to do this on your device as well. If not, I think I would suggest to do that, especially also to prepare for the upcoming exercise sheets or graded exercises. Let's continue with logistic regression, which is used for binary outcome variables for classification models. And again, the easiest part is here the estimation of the model, which would, if we would do it by hand, be the most difficult part. But we have a different data set here. It's a data set often used for intro to machine learning, which has risk factors of cervical cancer, so a type of cancer that occurs almost only for women. And we load the data, cervical cancer, and it's again in my file and it's in my folder and it's a CSV file, so I can load the data as easy as that. I have it here now. We have 850 observations of 36 variables. Let's see this here. Just a quick look at it. All right, this is the data set. I will upload the links for you to download this data. It's freely and easily available. And again, our by far easiest part is the estimation of the model. This time we call it model 2, so we don't get things mixed up. Now we don't use LM, linear model, we use GLM, generalized linear models, which means we first give the regression formula and then we specify which type of model we want to run. Our outcome variable is called biopsy, so there were biopsies done with female patients, and they were checked whether the cervical cancer was bad or good, malignant or benign, as I told you in the lecture video before. Then we use the tilde for the separating dependent variable from the set of independent variables. And I selected a couple of independent variables, so the woman's age, whether the person is using hormonal contraceptives, whether the person smokes, yes or no, and whether the person has been diagnosed with AIDS, and also whether the person has been diagnosed with cancer before. Again, we specify our data, so data, I just call it cervical cancer. And then, as I told you previously, I hope I didn't say this wrong in the lecture video, we specify the family of the model. And here, as we have the binomial distribution, it can only be 0 or 1, we use binomial. Don't forget the brackets here. We estimate our model. Okay, this worked. Nice. Now let's move on to inspecting the model. To get our coefficients, we can just use the coef function. And, well, this provides us with coefficients. We have an intercept of -18. We have some really high values, some really low values, some negative values, but as I told you before, we can't really make sense of these coefficients coming from the logistic regression model. So we could use the Stargazer package again to have this table a little bit nicer and maybe also see the significance, because this is important. We can use model 2. Again, we want the type to be text. If I select HTML or something like that here, it won't output something that we can make use of. I want confidence intervals. I want the confidence interval level to be at 0.95 again. Single row, let's set it to true again. And star cutoffs, I will just paste this in here because we did it previously. We want the significant stars to be on the same level. So if we can generate an output now, we can see that our binary variables, hormonal contraceptives no, hormonal contraceptives yes, are split up into kind of two coefficients. And we can see clearly that our model is actually not the best. Only one variable, which is the previous diagnosis of cancer, has a significant impact. This, on the other hand, has a highly significant positive impact. And this already sums up the interpretation of coefficients in logistic models. Let's state, it's important, we cannot really make sense of regression coefficient. However, we can analyze significance and direction. So we can say for TX cancer, it has a highly significant positive effect on the probability for a malignant tumor or malignant. Let's write it like this. What we cannot say is we cannot quantify. So this 1.9 is really a little bit useless for us. And we can say, for example, H has a H does not have a significant impact on our dependent variable. All right, but what we need or what we can use with logistic regression models are the so-called average marginal effects. So as I showed you in the short lecture video, the problem is that the impact of the independent variable on the dependent variable is not linear. It's not the same on the whole spectrum of the x variable. So what we can do is split up how the impact of independent variable on dependent variable is, split it up in infinitesimally small parts, and then just calculate the average marginal effect. So we just move to the right on the x variable for countless times, and then we would always look at what is the slope, and then calculate the average. And this is basically how these average marginal effects work. In R, we can estimate them by using the margins package. You need to download that maybe. And then we want our average marginal effects by, again, really easy. The function is called margins. So we give it our model, it's model 2. The type here is called response. And also we would like to see the standard error, so let's set standard error to true. And then, because we assigned it, we still need to print it. Let's look at the average marginal effects. We see these really, really small numbers. And the interpretation here is a little bit more helpful, but also not as straightforward. So an average marginal effect, in general, it represents the change in the predicted probability of the positive outcome. So the dependent variable to be a 1 instead of a 0. Associated, this is important, with a 1 unit increase in an independent variable. So let's say the age increases for 1 unit, so from age 25 to 26. Then on average, the probability to have a malignant tumor is really small, 0.06% higher on average with each year of age increasing. So let's try to interpret that for age and for cancer. Let's write averaged over all observations in a data set, 1 unit increase, which is which is the same as 1 year, is associated with an increased probability for a malignant tumor of 0.0, let's see, so this would be 0.6, this would be 60%, 6%, 0.6%, and we have 0.06%. Yes, this is, I think this is correct. Holding all other variables constant. This is again, so we have again on average, and we have the all other variables constant. For cancer, this variable can just take 0 and 1, so we can say on average CP individuals with, or individuals previously diagnosed with cancer had a 10 percentage points higher probability of a malignant tumor, which makes sense. And we can, what we need to write for both is this effect is not statistically significant, and we can write here this is significant on the 0.1% level. Alright, so this is how we can interpret the average marginal effects. This is much closer to the linear regression coefficients. We always need to talk about the probability here, but I think here we can make much more sense out of these numbers and not only the significance and direction of the effect. Alright. Now, if we want to visualize that, we can also again run get a coefficient plot. I think it's always a good and effective thing to do. Let's do this by doing the coef plot and just model 2. I think we can just do it without any specifications for now. And we can see that most of these variables are really non-significant. The only one would be the previous cancer. Fortunately, because we have incredibly high confidence intervals, the x-axis is spread really widely, so we don't really see how far this is away from 0 or not. So actually, maybe in this case, the coefficient plot isn't the best, but what is maybe more interesting would be the ROC curve. And here we have a new package, again, it's called PROC. And first, so what we want to see is what would be the optimal cutoff for a model to increase the true positives and decrease the false positives, if our model is asked to predict malignant tumors. And first, what we need to do is we predict the probabilities. So we use the predict function. We give it our model, and our type again is response. So we did our predictions with our model now, and now we can use the ROC curve function. No, actually we have an object, we call it ROC curve, and the function is called just ROC. Our response is our dependent variable. It's the cervical cancer dataset. Variable is called biopsy. And our predictor now are our predictions that we did in the last step. So this object called prop here. We do this and then we plot the ROC curve, our object. Let's just try like this. Wait a second. Did I load the package? Maybe that was the problem. Yes. And now we plot this and we get our nice ROC curve. We have the specificity and the sensitivity. So, and see here the x-axis is flipped because specificity you want to be here, you want it to be as low as possible. And the sensitivity, or let's say, actually I think these names are wrong. If we flip the axes, we should better rename it. Let's do this. I think it's better. We label the x1 with false positive rate and the y label to be a true positive rate. Because if you flip the x-axis, all right, like this, you want sensitivity and specificity, of course, to be as high as possible. But let's, you can ignore this for now. We want the true positive rate, so true cases, malignant tumors that we also classified as malignant, to be as high as possible. Optimally, of course, 100% of the tumors we also, or of our positive predictions were also positive in the data. And false positive rate, so people that actually had benign tumors, but we predicted a malignant one, we want this to be as close to 0 as possible. So here we can see how the trade-off between false positive and true positive rate shapes throughout the cutoffs. And here at the end, of course, we maximize for false positive rate and for true positive rate, which is good. All right, and then what can also be important, but in this case it's a little bit unfortunate again, to look at the marginal effects and by plotting it for one independent variable, because I told you it's not linear. It through the spectrum of the x variable, the marginal effect changes. So we would optimally, if we want to understand that, try to plot it. We have a new package here, a lot of new packages in this video. It's called effects. And let's look at the effect for age. We call it HFF, and the function is again called effects. We specify our variable, it's called age, and our model, it's the model 2. Let's load the package, let's run this. And now we can plot this by just typing plot HF effect. And now, unfortunately, we see that age had such a small effect that we can't really see a difference. But here, this is what I wanted to, this is what I meant with the spectrum of the x variable. So it could be that the effect of age had, for example, a different shape, like a U-shaped or something like that. So it doesn't necessarily need to be a linear effect. Here it seems like this. We see a very small cut here. I don't know if you can see this. Let's check this. It's here, but I think it vanishes. But this is in general how you can plot the marginal effect of one independent variables on the dependent variable of the biopsy here. All right, so this was estimating logistic regression models, interpreting the coefficients as much as we can, then the average marginal effects, and then plotting coefficient plot, ROC curve, and the marginal effects plot. I think here it's important to state we didn't have the best or most interesting results. The model was also not very good, but I think this is also a good example why this data is often used for machine learning applications, because I think this logistic regression model is maybe not good enough to pick up the complex patterns in the data. So I think this can be used really nicely to run ML models, but maybe not a simple model like this with only 5 independent variables. All right, thanks for listening, and see you in one of the next videos, or hopefully also next sessions.